Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm very happy to have Simon Müller with us today. Hey, Simon.
Hey, thanks for having me.
Good. What's your geolocation? Where are you at?
So I'm staying in my flat right now, as I guess many people, and that's close to Zurich, not in the city of Zurich, but
Okay.
basically around the suburbs. Zurich, Switzerland, of course.
Cool. I think you have the honor of being the first one from Switzerland
Well, that's good.
on this series. So that's very cool. Very cool. That is an awesome picture over your left shoulder there. I like those plants. Very good.
Yeah, there's a story related to that. I got this with my partner when we were on vacation in Sweden, and we just really liked it, and then we brought it back. So
Very nice. So those are native plants to Sweden?
yes, exactly.
Which means they come up in the spring or so. Because growing season's kind of short in Sweden, I imagine.
Yeah, I would imagine so.
Yeah.
Depends on the latitude, but yeah, generally short.
So are you going to the office these days? Or
Well, I haven't really been. So the official sort of not just recommendation, but we are supposed to stay at home and work from home.
Yeah.
So that's probably for the next month at least, and maybe longer. But we'll see.
Yeah.
We'll hope it will get better, but
yeah.
We'll see.
Hopefully we'll blanket the globe with some vaccine here, and
exactly.
That'll be a good thing. Very cool. So Simon, what do you like to do for research?
So I like to investigate giant planets, and that includes giant planets in the solar system, like Jupiter, and more recently also giant planets in general. So that includes exoplanets, and I do theoretical models. So I don't do observations, and that basically means we do numerical modeling of these planets. And so I'm a PhD student in my last year now. So I'm supposed to graduate in the summer. So
well, congratulations on being very close to finishing, Dr. Müller. That is awesome. Very cool.
So in sort of the beginning of my PhD, I focused more on Jupiter, and we there basically focused on trying to explain Jupiter's interior as it is sort of inferred today from observations, so from the Juno mission. And we sort of try to explain its interior by doing evolution models of giant planets, of Jupiter. And so that's sort of where I started. But then as time goes on, we sort of wanted to expand our knowledge also towards exoplanets and then just in general giant planet formation and evolution theory. And that's sort of I guess what leads me to the paper we're going to be talking about today.
We will. So let's go ahead and get this really lovely article. This one's an APJer. And theoretical versus observational uncertainties, the composition of giant exoplanets. And Simon, take us away.
Right. So this is work we've done together with my supervisor, who is Ravi Telet, and actually a master's summer student, Maya Benyami. So she was here at our institute for a summer, and it's largely based on work that we did together, and that was like a really fruitful visit. So I'm super happy about that.
Good.
And so the idea of this paper was, now that we basically had all this knowledge built up and these tools to evolve Jupiter, and we've tried many things there. We've tried different equations of states and so on. So we sort of built up a repertoire of things we can do in these models. So then we thought, okay, we know that there's many parameters that go into these models, in these theoretical models. And people use them, and they often maybe try like one or two different things, and then they sort of present their results. But it's not clear exactly what would happen if you tried many more, or if you tried different ones. So here we basically almost wanted to take one step back and really start at the basics. And so it's sort of the most important, we think, or at least very fundamental parameters in these giant planet evolution models is one is the equation of state that you use.
Uh-huh. Yep.
And that's the equation of state for both hydrogen and helium and whatever rest there is. So that's what we call the heavy elements, which is just anything but hydrogen, helium. And then others are, for example, the atmospheric model that you would like to use, or the opacity in the atmosphere, and so on.
Right.
And so that was sort of the setup we had in mind. And why does this matter? Because so one thing we theorists really like to sort of get a good handle on is the composition of these giant planets, because that tells us something about how they form, right?
Yep.
Because we have many formation theories and like details of formation theories of giant planets, and one of the very popular one is the core accretion theory, where we basically, just to summarize, we basically think that at the sort of primordial stage of a giant planet, before it's like while it's starting to build up, it's basically at the start just a pure heavy element core, or mostly heavy element core, at maybe like 10 or so Earth masses. And then it basically gradually starts to grow and grow. And then at some point it becomes heavy enough so that it can accrete some gaseous envelope. So that's hydrogen helium gas. And then if at some point the envelope mass is about similar to the core mass, then it starts to go into this runaway phase where it really starts to grow rapidly, where it just starts to accrete lots of gas. And then at some point it is a giant planet. So that's sort of our, I would say it's the most popular theory right now, probably, of how we think most giant planets form. There are some alternatives, but I think that's not the topic for today. So we sort of focus on this idea that you start with a heavy element core, it's like a small sort of primordial planet, and then you accrete a gaseous envelope on top of that.
Yep.
And so now I talked about this core, and I said it's mostly heavy element, and that suggests something about the composition of these planets. And it also suggests that the heavy elements play a major role in the whole formation, because if you cannot build up that core, you cannot build a giant planet, basically. And so what people have been doing, they basically wanted to study the composition of giant exoplanets. And the way you do that is, since you cannot measure the composition, I mean, you might be able to get the atmospheric composition, but usually, I mean, that's for the future. We have a few atmospheric composition measurements of giant planets, but they're few and far between. So what you do is you take a planet that has a measured mass, age, and radius, and then you use that mass and age, and you try some different compositions, and you can see which compositions give you sort of the observed radius.
Okay.
And you say, at that point, you say, okay, we think that's the bulk composition of that planet. And now that basically leads me to these parameters, right? Because that, of course, depends on the parameters you use in your model. And that's sort of the challenge we have here, right? The challenge is from observation, we basically get mean densities. We get radius, mass, and age. And then we want to infer composition or bulk metallicity, and that's extremely challenging.
Yes.
And I think uniquely challenging for giant planets is because, of course, for example, rocky planets, as they evolve, they don't really change their radius much unless they have like a big gaseous envelope, because of course rock is not really that compressible. But for gas giants, since they're mostly hydrogen helium, as they age, they cool down and they get smaller and smaller. And so you also have this sort of the time factor that's really important. So that's the age of the planet. And of course, age measurements for planets are usually highly uncertain, because we basically just take the age of the star, and that's usually also highly uncertain, right? And then you see there's many things that make this really difficult. So that's the basic game we're playing. We have we have a mass and radius and the age measurement of a planet, and then you try to infer the composition.
Mm-hmm. Yep.
So, and now in this paper, basically, we wanted to see how that inference of the composition would change if you use different equations of state for the hydrogen helium, if you use a different atmospheric model, and if you use different distributions of the composition in the interior.
Mm-hmm.
Because so sort of in the classic idea, people thought of giant planets to be either homogeneously mixed, so everything has the same composition in the whole interior, or it's like a core envelope structure. So you have a heavy element core, maybe like 5 to 20 Earth masses, and the envelope is essentially metal-free or likely like stellar composition. And that's sort of the two sort of boundaries you have. Of course, now in a more modern view, we think it might not necessarily be that simple, but actually there might be composition gradients inside of these planets and so on. But that's basically the two boundaries are either like you have a core envelope structure or you're fully mixed. Yes. But again, it's a simplified model, likely.
Uh-huh. I'm with you.
So the first thing we basically want to do, since we in the last few years we basically we introduced a new equation of state into the stellar evolution called MESA, and we did that because so MESA as it is right now, it has an equation of state that can model giant planets, but only it doesn't really model the heavy elements. It models the hydrogen helium with the SCBH equation of state, but if of course these giant planets have high metallicities, you would like to have an equation of state for the heavy elements as well. So that's sort of the work we did to implement such an equation of state into MESA, and it allows us to use MESA, which again is generally made for evolving stars. We can use it to evolve planets as well. With a self-consistent equation of state for the heavy elements.
Cool.
So that's the tool we use to do these evolution models. And so for maybe for people who are not familiar with evolution models, so these are 1D models. They basically assume that the planet is spherical and in hydrostatic equilibrium at all times, and then that allows you to follow these planets as they cool down. And of course, if you say cooling, then you also have to say something about the energy transport in the interior, and that's in general by either convection or conduction for us. And that gets decided by this very famous Ledoux criterion. So I think for the methods, that's sort of I think a good point to start on. So the first thing is, now that we developed this tool, we basically wanted to see whether we could confirm previous work on the inference of the composition.
That's a good idea.
And there is this famous, I would say famous, it's quite well known in like the planetary community paper, Thoringer et al. 2016, where they basically for the first time really did this quite thoroughly, where they built a catalog of planets of giant planets with measured mass and radii, and they inferred compositions. And they came up with a fit of mass versus metallicity. And I think now you can go to the first figure. So we can talk about that. So it's a bit of a busy plot, but I'll just go step by step. So on the x-axis, you can see the mass. So that's the mass of the planet. It's measured mass, right? And on the y-axis is the planetary bulk metallicity. And that's the metallicity inferred from models, given some parameters. And then the size of the dots corresponds to the radius and of the planet. And the color is the stellar Fe over H, so it's the stellar metallicity.
Okay.
So basically what Thoringer et al. Did, they built this catalog and they inferred the bulk metallicity of these planets. and then they basically try to fit a line, basically saying you can see a trend. So as you increase your mass, your bulk metallicity goes down.
Right.
And that sort of, in a way, makes sense for giant planets, right? Because you're saying you're mostly hydrogen helium, you have a small core. So it sort of does make sense, like if they have a similar mass core, that your metallicity would go down. And maybe just to define metallicity, it's basically just the fractional mass of heavy elements in these planets.
Yes.
Just that we're on the same page.
Uh-huh.
So their main result was that as these planets increase in mass, you have a slight downward trend in bulk metallicity. And it was sort of interesting, but you can see there's a large scatter in this. Like that's one thing you can see. So while there's a clear trend, you have a large scatter. That's one thing. And so you see this black line is basically their mass metallicity fit. And then we sort of wanted to overplot these different colored lines as well, which basically would show you how the planetary metallicity is if it scales with the stellar Fe/h.
Okay.
So now the interesting thing is, if you naively you might think, okay, a giant planet might actually, its metallicity might actually scale with the stellar Fe/h as well. But in this plot, you can see that's not really the case, because if you, for example, look at one of these colored lines, just pick any one, right? And then you can see on this line lie planets with different colors, which means they have different stellar Fe/h.
Uh-huh.
And if they lie on one line, the sort of the fit would tell you that they should have the same, right? They should be the same color, but they're not.
Right.
And it's just, so we're not the first ones to sort of notice this, but I think we just thought this is also a nice way to sort of show it, that the sort of naive assumption that these planets might simply scale with the stellar Fe/h is not true. So the main takeaway from this plot is that we could, while we had differences in sort of the inferred metallicity compared to Thorngren et al. 16, we basically could confirm their fit. We got a very similar fit. And so in a way, that's very nice. It's nice to confirm results, of course.
Very good.
But I think now you can go to figure 2.
Okay, slide down. And figure 2. There you go. Oop, a little too big now.
So I think the more interesting one is the top panel. So what we wanted to show here is basically, and it's also been noted by different people, is that it's okay on the leftmost plot in the top row, you have again mass, and now it's called planetary metallicity enrichment, which is basically how enriched you are compared to the star.
Okay.
It's basically metallicity of the planet over metallicity of the star.
Okay.
And now you see, again, you see this black line, which is the fit line, and you show as you increase in mass, this goes down, that we've seen before. But now I've talked about before is how we think these giant planets form, and they should all form with some sort of core, with some sort of heavy element core. Now, the interesting thing is, if you could think that actually from formation, it seems to be that they could have similarly sized cores, these planets. Now, so the game you can play is you can just remove like a 10 Earth mass core in the metals basically, and see, okay, now that's just your envelope, right? And you can see that as you start to remove this core, the correlation starts to disappear.
Yep.
And this sort of suggests that actually if these planets have a same sized core, then this trend actually disappears. Again, we're not saying they do have that. It's just an interesting thing to note.
Yes.
And that sort of just tells you that actually the reason why you see this, why you have this mass metallicity trend, is because your core to envelope ratio changes. That's sort of the way we see it. And it's not because there's like an inherent scaling, right?
Yes, I'm with you.
so in that sort of I think that's sort of the games you can play with this data, but this is, so far we've basically just looked at this catalog of planets, and we sort of just want to see, okay, can we find anything new? Can we confirm the previous results? And as I said, we basically get the same fit. But now we really want to get into the sort of gritty details, which is again, how do all of these different parameters change things? So let's, I think, first look at the equation of state influence. So I think that's the next plot, I think figure 3.
Indeed.
Okay, good. So this is like a typical evolution plot of the radius of a giant planet. As you can see, it's age on the x-axis and radius on the y. And so this is for one particular planet, I think it's 0.4 Jupiter masses, where we basically just let it cool down over, you see, like the age of the universe, pretty much, so 14 gigayears. And so you take a planet of a given mass and you give it different compositions, which are the different colors in this plot. So I think blue is metal free, and then up to red, which is like 30% heavy elements. And so you see we have dashed lines, which is where we use the SCVH equation of state for hydrogen and helium. And then we have the solid lines, which is an updated version of this SCVH equation of state, which we call CMS. It's basically, it was released in 2019. So, and you can see it's very different. You can see there's actually quite a drastic change in the radius of these planets. So if you, for example, just compare the dashed blue lines, you can see that they are quite far apart. I would say like 10% or so, at least in radius.
Yes.
So, and that tells you basically, okay, you're just using a different equation of state of hydrogen and helium, and you're already getting a very different radius at a given age. So that's, yeah. So that just tells you that you need to be careful about this. So if you, and I think the implications you can see in the next plot the best. So here it's a mass radius plot. So mass on X and radius on Y. And now we're not looking at real planets. So the real planets are basically those with error bars, but the lines are basically just coming from our models. So we take a planet at a given mass, and we impose a composition and then basically come up with this mass radius diagram. So again, the different colors are metallicities going from 0 to 20 to 40%. And the dashed line is again with SCVH equation of state of hydrogen and helium, and the solid lines are CMS. So it's
okay.
version. Now, if you look, for example, at, let's say, at like the vertical line at half a Jupiter mass, you can see the sort of orange line and the blue line, the orange dashed line and the blue solid line, they cross.
Yes.
And that's the line basically of either 0 metallicity or 20% metallicity. And that tells you, depending on the hydrogen helium equation of state you use, and we're just comparing 2 ones, there are more, then you could either infer this planet is completely metal-free or it's 20% heavy elements.
Little difference there.
There's a slight difference, right?
Okay.
And you can see this is, and that's why you overplotted these real planets. It matters, right? Because we do have planets that are sort of, the uncertainties are within that range, right? So for many of these planets, depending on the equation of state you use for hydrogen helium, you could infer a very, very different composition. And I think that's the main takeaway from this plot. Okay. Another thing to note is, in general, this new equation of state leads to smaller planets. And that's because it gives you a denser hydrogen at some pressures and temperatures. That's sort of the reason why this happens.
Okay.
And so yeah, the sort of the summary of this first part is, so equation of state matters for hydrogen and helium, and it can really, really change the inferred composition of these planets.
Right. Okay. I'm with you. Yep.
And so the next thing we wanted to look at, which is again a very sort of fundamental parameter you use, is the opacity, the atmospheric opacity. And hand in hand with that is also whether you assume a fully mixed planet or a core envelope structure. Yeah, I think this plot is a good one to show. So maybe just to reiterate again, so we have these two internal structures that we look at. One is completely mixed, so heavy elements are just everything the same throughout the planet, or we put all the heavy elements into the core and just assume a stellar metallicity in the envelope.
Okay.
So that's sort of the two extremes. And now, of course, if you assume your planet is fully mixed, then your atmosphere should also be enriched in metallicity, and quite drastically sometimes, because you saw in the previous plot, you saw that some of these planets have like 50, 60% heavy elements. So the atmosphere could be enriched quite a lot. Now, a lot of the previous evolution models, they did not take this into account. They basically just used solar metallicity atmospheric models. And that would drastically underestimate the opacity you have, because if you have more metals, you become more opaque for these gas opacities.
Yep.
And so basically that's sort of the game we played here. So we took these planets of different it's two different masses. So in the top panel is 0.2 Jupiter masses, in the bottom one Jupiter mass. And then we evolved them with different bulk metallicities. And in the dashed lines, we assumed everything is in the core, all the heavy elements in the core. And in the solid lines, we assumed that we have everything fully mixed. Now, if you look at the dashed lines, that's sort of what you naively expect. As you put more metals, your planet becomes smaller and smaller at a given time. Right.
Yes.
Sort of, you have more dense material, so you expect a smaller radius.
Yep.
Now, the interesting thing is if you look at the solid lines, they have a different behavior. Now, the different colors are for different stellar fluxes. So as given in the legend. So they can be quite high, but many of these planets are, of course, irradiated. So realistically, they are receiving flux.
Yeah.
And that just means your atmosphere is hotter in general, because these are oldish planets we look at, right? So it's 0.5 gigayears and 5 gigayears. So they're pretty old. So if you don't have irradiation, their atmosphere will be pretty coolish usually. Now, the thing is with the atmospheric opacity, the gas opacity, it scales more with metals the hotter you are. So if you have a really hot, atmosphere, yes, you have a strong scaling with metals. And if you have a cold atmosphere, you don't really scale with metals.
Got it.
And that you can see in this plot, right? Because if you look at, for example, the 10 to the 7 or 10 to the 8 lines, so that's these greenish lines, you see that at first, as you add metals to the planet actually becomes bigger at a given time and not smaller, which is a bit counterintuitive, right? But you can see it doesn't really happen if your planet is not irradiated or not irradiated strongly, because its atmosphere is just too cold. So basically the increased density is just stronger.
There you go.
But for the others, so if you have a higher flux, so if your atmosphere is hot, you can see you have this turnover point. So as you add metals at first, your planet actually becomes bigger at a given time, and then it starts to become smaller again at some point. We thought that's really interesting, and it hasn't really been, I think, shown in this way before.
Right.
And it shows you that what you assume in sort of how these heavy elements are distributed matters again, right? Because you can see it's large differences in radii, again, up to 10, 20%.
Yep.
Between these models.
Comparable with the observation.
Right. So now we basically had these results that we showed, okay, we have, like, depending on these equation of state and the atmospheric model, you get 10, 20% difference in radii or more. But of course, how does this compare to observations?
Okay.
And I think, I think we can go to to this plot before we go to the last one. Maybe just take one step back. So before I said, if we use this new hydrogen helium equation of state, we get smaller planets compared to SCVH.
Yes.
Now, the interesting thing is actually found a lot of planets where if you put 0 metals, so it's basically a hydrogen helium planet only, it has 0 metals, so no core, which is sort of hard to explain in core accretion. But so if you put 0 metals and we evolve these planets with these parameters, with their stellar flux, with their mass, we actually find that these planets are inflated. So they are too big.
Yes, the gray obstacle above the line.
So it's in all the panels, it's age versus radius again, and for different planets, right? So if you, for example, look at, I mean, you can pick at any one, so you can look at like Kepler 89d on the top right. So you can see if we model the evolution of Kepler 89d, you see its measured radius and is basically larger than what our models say, which means that there is some sort of inflation mechanism going on. Right. So if you use like a standard evolution model, you would predict a radius that's too small for this planet, even if it's fully hydrogen helium, which should be like the biggest planet you can have.
Okay, good. Yes.
So we're not saying it's impossible. I mean, we believe these measurements, but what we're saying is that if you just use these standard models, actually you might run into some problems. There's some explanations of why this could be the case. For example, they could have an enriched atmosphere, as we just saw above, right? That can puff up your radius because you're delaying the cooling.
Yes.
You're more opaque. Or they could have composition gradients if we in the interior, which could again delay your cooling, because actually, while we sort of the standard picture, people think giant planets are fully convective, they might actually not be. They might have composition gradients, and so that could delay your cooling as well. So that's some of the explanations you could have. So we're not saying like it's impossible that they are this radius. We're just saying they are somehow inflated beyond what you would expect from like a simple model.
Okay.
So that was sort of the neat side effect of these investigations.
Cool. Very cool.
So as I said before, so one of the main things we wanted to do is really to see how do these model parameters compare to the uncertainties that you have in measurements. And I think the important plot one is here is figure 8. I think it's
money plot.
It's
Slightly smaller. Okay. There you go.
Right. So basically, again, it's a mass radius diagram, and we overplotted some planets and their uncertainties. And the shaded regions are basically, it's sort of the region that our models predict for a given mass, right?
Yes.
At a given age, at a
Yes.
given age range, so between 1 and 8 gigayears, which is the age range of these planets, essentially. Like they are within that age range. And you can see we have, again, these overlapping regions in these error bars, right?
Yeah. Mm-hmm.
So again, because our different models give you very different results, you can have these, like, the planet can actually be, if you, for example, look at Kepler 420b, it could actually have all of these compositions. So it could either have 0 metals, 20% metals, or 40% metals, depending on what you use for your model.
420b. Okay. Yep.
Right. It has a large error bar, this one. So of course, it's an extreme case. But so maybe we can go to the next figure, so figure 8, which is sort of the main, I would say, the main result.
Okay.
What we did here is, so it's always, so the y-axis is radius, and the x-axis doesn't really mean anything, it's just different spacing. So you always see in each of these planets, in each of these panels, we look at a different planet. And so this planet has a measured mass, which is pretty precise, and it has a measured radius, which is usually precise as well. And then we take a metallicity range from the literature that has been inferred before.
Mm-hmm.
And then we basically use this metallicity range for 3 different models that we have. So, and that's the 3 different colored dots. So the gray area gives you the measurement and the associated error. And then the blue one is SCVH, equation of state for hydrogen helium, fully mixed. And then the red one is CMS equation of state and core envelope, and then blue is CMS fully mixed. So it's 3 different models basically.
General. Yeah.
And so what you can see is that the difference between these different colored dots, so the different models, can be much, much larger than the measurement uncertainty.
Mm-hmm.
So for example, a very extreme case is the top left panel. I forgot which planet it was.
Top left, that's Kepler.
Right, so it's really extreme. So it's actually, it has a quite precisely measured radius, but the different models would give it a very, very different radii at this metallicity, which tells you that actually this inferred metallicity is not actually it's not constrained that well. Like it shouldn't be pretty much unconstrained if you include that these models have different parameters and so on.
Good.
And so, and you see for some planets, of course, all the different models lie nicely within observational errors if the error is large. So for example, Kepler 40 or 20b, right? So that's fine. But I mean, in general, of course, there's this extremely large effort of people to push observations to higher and higher accuracy. So we see there's smaller and smaller error bars on these radius measurements, and we have new missions that measure more planets more precisely. But at the same time, I think we're now at a point actually where theory lags behind.
Okay.
And the problem with that is, of course, so you can get like hundreds of precise measurements of these planets, but if we don't really understand the theory that well, how are we going to interpret it?
Mm-hmm.
And how are we going to learn about how these planets form if we cannot constrain their composition better? And that's sort of really the main point we wanted to make in this paper, is that we are now at a stage where we really need to progress in theory. We really need a big push to develop theory further, so that we don't fall behind with observations.
Mm-hmm. Okay.
Because in the future it will only get more complicated, because we have, for example, the James Webb mission coming up, or the Ariel mission of ESA, which will actually give you hopefully atmospheric measurements of giant planets. And of course, but if you cannot even constrain things with the models we have now, that will just give you more questions. Right. So
very good. Okay, cool. Nice work.
Thank you.
Awesome work. Very good. So let me ask, let's do a little future look. So where do you think over the next, say, 5 years, is there, you sort of intoned it a little bit. So are there new efforts in trying to make the equation of state more precise? That one seemed like a fairly big project. Are there new efforts to try and do hydrogen helium dominated equations of state, the metal distributions within there? So yeah, where do we go over the next 5 years or so? Where do you see things going, or would like to go?
So in terms of hydrogen helium equation of state, I mean, there's many people working on this, and it's mostly actually motivated by the solar system planets, mostly by Jupiter, because there, in a way, Jupiter is a test bed for these equations of state, as well as we need really, really good equations of state to explain Jupiter's interior, because we have such precise measurements of its gravitational field that actually uncertainties in equation of state can basically mean that you cannot interpret the data. So people are now, I think, more and more starting to compare the equations of state for hydrogen helium that we have, and of course always developing better ones. And if I say better ones, it basically means they're based on more complex simulations. Often it's called density functional theory, what these people do, that build equations of state. And basically these simulations are getting better and better, and people start to compare more and more. So I feel hopeful that in terms of hydrogen helium equation of state, we will get to a point where at least we can agree which ones which one we should be using, and of course, and that will help for sure.
And for those who might be curious, Jupiter's sort of reside in sort of this here be dragons region of the equation of state, where it's, warm, dense matter.
Right.
All the effects come into play. It is the quantum system. It is a body system. It is partially pressure ionized, and so there's this region in the density temperature space, or here be dragons, and this is where Jupiter lies, is here be dragons, and so it's a tough area to do. It's not super clean, and so this is sort of the origin of our uncertainty and equation here. Very cool. Very cool.
Right. So, and I think one more thing that I'm hopeful and that should be done is, of course, so for the heavy elements right now, we usually just use one stand-in. So we usually just use, okay, all the heavy elements are water, or they're rock, or they're iron, or a water-rock mixture, and so on. But of course, in reality, we know that that's not the case. And so that's really something also I hope that can improve in the next few years. But it's also a tough problem. It's a tough problem to solve. To have like multi-component equations of states. It's not easy.
Right. Well, that just makes it'll be interesting over the next 5 years. There's lots of
So
great
there's enough work to do. There's enough work to do for sure.
So then maybe that'll be something for you to attack once you're post Dr. Müller.
Right.
Very cool. Simon, I want to thank you so much for taking some time and sharing your lovely APJ article with us today.
Yeah, it was my pleasure. It was great to be here.
All right. Thank you, everyone. And we will see you on the next one. Bye-bye.
Bye.